Five. Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my x86 operating system written in Rust. So its current features is like it boots, it can do a little bit of like network, memory allocation, serial, VGA logging, unit testing, it can like work with the clock, it can work with PCI, etc., etc. But we don't have like everything we need yet. There's no like user space. It only boots on x86. It only runs in QEMU probably. We haven't really tried on hardware. But what we do have is like if I run the OS, this will like boot my kernel in QEMU right out to the VGA. Do some stuff where it like this is like a demo where it's trying to initialize a TCP connection. So if we try to like netcat into this guy, we can see that like I do in fact like initialize some form of TCP and write some data that it sees. It's seeing the word test. But if I look at the Wireshark capture, hold on, I can dump the network from inside the VM. Sorry, let's try this again. And we can see what the network of the OS is seeing. And so where we're at now is if I look at that dump, which will be somewhere in here, this guy, we'll see that like we do indeed do like a little negotiation. We get like a syn, this guy sends us a request, we send back an ack, and we send back a syn-ack, he sends back an ack, and so we've done like the TCP handshake. And now we're like ready to start receiving data, except we're not acking any of the messages that come in. And since TCP is like a reliable protocol, they need us to like the Linux side who's sending a packet, he needs us to say like, yep, we sure got it, and we're ready for the next one. We haven't got there yet. So what we did like last stream was we kind of set this like kind of like demo proof of concept to understand, like make sure that we're like parsing TCP frames, we're like transmitting them correctly, and we like understand at least the like initial handshake. And what I wanted to cover today was trying to kind of like formalize this and maybe handle like correct, like if we could get a little farther down the road and maybe handle receiving TCP packets reliably, i.e. acking them correctly. I think that would be kind of chilling. I'd be kind of happy with that. So let's take a look at that and see how far we can get. So what we have right now, let's just kill this guy. Or maybe we'll do what we did last time and we'll make a loop in the background that's just going to like spam TCP connections to our OS. And that way, when we boot, we'll be able to see what's going on. And maybe we should have him punch some data in there so we can see where we get. So where we got yesterday. So somewhere, let's draw a diagram. So we have our Ethernet driver. I guess we write the word first, Ethernet. And he is like connected to the kernel. Does this diagram make sense? We'll see. And what the kernel does is he feeds in a like handler. He has like a on packet, we'll call it. And what happens is every time the Ethernet card receives a frame, he calls this like on packet. And this on packet, he sees that we get like Ethernet frames, an Ethernet frame, and this is Ethernet. And inside that, there's another like an IPv4, and inside that there's TCP. And right now, what we're doing is we're just kind of like handling this like statelessly. So we read this TCP frame, we see that it's a handshake request, and we just from here immediately like call back into this guy with the appropriate ACK. But what we really would want to do is, let's open up like dummy RS. We probably want like in our main function or some like, what are we going to call this? Like handle TCP. We'd probably want to connect this to someone else, right? So we have like function TCP server, we'll say, and in here we kind of want to do something like we'll take in a kernel here, and let's just disable the language server right now because this is like pseudocode ish. We don't want these errors, so we would like take in a kernel, and we'd want to say like let socket is the kernel, like maybe like we have like a TCP element in there, and we might want to like create a socket here, right? And here we would pass in like our port number, which is like 1,000, like we'll say like 6,000 for the port number, and maybe like the IP address that we're listening on, or the Ethernet device. Not sure, right? So we might say that like, we might want to say that we're listening on our IP, which would look something like this. And this would give us like a socket, and we might want to do like a socket. What do you do here? This is like a service that many connections from TCP will come in to. And each TCP connection is like a combination of my side and their side. So if like 100 people connect to the same socket, we can talk to them all. So we'd actually want this to be like, we'd probably get like a connection from here. So we'd want like, we'd say maybe for connection in socket connections or something. I'm just spitballing, right? So we could say that like every time that this guy gets a new connection, he returns a new element. And in those, for each of those connections, we might want to say like, if say we were a web server, right, we would want to say like connection, we'd serve HTTP requests on the connection or something, right? Without really thinking about what this is. Now, what's weird here is that this connection, this is going to be like something that is port specific, right? So this is going to have something like, it's going to look something like remote IP is going to be something, and he's going to have like remote socket, and he's going to have like maybe my socket on my side, like local IP, local socket, maybe, right? I'm not really sure. And this is like completely, this is like, how do I say this? This doesn't care about any of the like implementation details of TCP, right? This only cares that like, if I'm working with this guy, I want to be able to like write like connection.write hello. Like, what do I say here? Like, web page. Want me to tell you about a joke about TCP? I've heard this one. I know where this is going. So, sorry, brain's melting. So yeah, we're gonna like want to like write something in this connection from like the user's perspective, but that actually is like quite involved, right? Because when we write something, we want to make sure that like we're gonna have like a buffer of outgoing packets, and if the outgoing packets, like if they're not acked by the other side, we're gonna want to resend them. But all of that, like, we don't want to keep track of that here. All we really want to do is we want to say like, I'll wait for that to finish. And when this finishes, like this is only going to finish once the other side is acked, probably. So there's going to be like some like extra context that needs to happen in here. And also, like, how do we detect that the other side has acked? It's going to be a little more involved because, or how do I say this? We need some way to go from our Ethernet driver back to this connection, right? Because in our Ethernet driver, we're just going to have like on read packet, and this is going to be like a Ethernet frame. And we're gonna like eventually do some parsing in here, and we're gonna get into a TCP frame. So we'll have like TCP frame is equal to packet something. So we'll just say like this is like get frame from packet. And somehow we need to dispatch this back over here. So I guess we would need some sort of channel. Okay, I'll tell you a TCP joke. Okay, let's hear your TCP joke. So I guess like what this would mean is who does like the acking here? So part of the ack, we need to have like a sequence number associated with this. Maybe that lives in here in the connection. So he'd be like, what's my current seek num? And he'd probably have like an ack num as well. And so here we would need to do some sort of like lookup, right? We need to say like, we'd have some like registry of connections, probably. And we'd say like registry lookup our TCP frame. We'd look up like the port probably and the IP. So this would be like the source IP of the request. And then once we have done that, then we can like ack there, the connection. So we can say like generate, we'd like generate the ack for the given frame. But this guy would need to keep track of if we're allowed to ack it, right? Because in TCP, if you receive like packets 1, 2, 3, you're not allowed to ack packet 5 until you receive packet 4. So this is going to require some sort of state. So maybe this actually uses the connection itself, because he also has to generate using like the sequence number and ack number and all that stuff. And which means that this guy probably has to keep track of like, he has his latest ack num, so he can like check if, or he has the latest sequence num he's received, and he can check if he got it or not. That seems reasonable. I don't know if there needs to be some sort of buffering here, where if they give me, if I receive like 1, 2, 3, 5, 4, I don't see any reason why I shouldn't be able to be like, oh yeah, I did receive 4, 5, and just lie with the order I got them in. That doesn't seem crazy, but I don't know if that's normal, etc. So probably for now, we'll just assume, we'll do like the naive implementation, which is we'll say we have to receive them in order and we'll just force the sender to resend. Sure. And then once we've like generated that ack, we still need to like somehow over here, like propagate the data over to this side. So we would probably say like TCP frame, get the payload from it, and we have like a channel in the connection that we can send data to and from, right? So we'd have like a TX, and that kind of would let us propagate the data, but handle the actual like details of TCP on the, like not on the user side. And I think that's reasonable, because say that we weren't like currently waiting on this. From the OS's perspective, we have like still received the data, and it makes sense to ack it before this guy's like done any processing of the data inside. So I think I'm like okay with this structure. Maybe this like overloading of connection doesn't really make sense. Maybe we would call this like TCP state on this side, and this would be TCP state, and our connection, TCP connection would be something just like a channel that's like receiver of evacuate, which does force a copy. So maybe not. That's pretty reasonable. I don't know. I'm okay with copying for now. Maybe there's a cleaner way of handling this where we use the buffer directly here. If you could have some sort of like way to transfer the data as a slice, So instead of like having this like asynchronous thing going on, you could maybe just call a callback. Let's think about what that would look like. So this guy, instead of having like a receiver, he'd have a callback that would get shoved in here probably. And this would be like a function that takes in a slice of U8. And then this guy, instead of calling send here, he would just call the callback. And then what does it look like on the user side? What does it look like here? The callback. So if I want to do this asynchronously, I think I have to allocate a buffer and send it that way. If you want asynchronous, you can make it a C++ style state machine. C++ 20 style state machine. What does that mean? Let's take a look. C++ 20 state machine. Oh, I think that these are basically, if you're talking about like coroutines, I think that these are basically the same thing. Let's see. Yeah, you like have like a generator that generates data, I guess is what you're thinking about, like a coroutine that yields things, and I would be like yielding buffers. But I think that we're kind of in the same problem there, that if I want to like avoid an allocation, I don't know if I can do that. Oh, async IO, not coroutines. Async IO C++ 20. Let's see. So what does this guy do? What does this say? Run results is this. TCP echo. Let's see. So he takes in a string view of the message. That is what I kind of want, is I don't want him to take in like a buffer. I want him to take in like a reference to a buffer. So you open a connection, and oh, but this looks like we're kind of in the same thing. The fact that this guy's writing stream buffer and copying the data, I bet that that's a data like a copy again, because it makes sense, right? Like if I'm from my driver, basically if it's struck with an enumeration of state and a completion of callback function pointer. Oh, okay, a completion callback function pointer. That makes sense. So basically I say that like I'm going to give you this data, and when you're done, you have to tell me, like you have to do something to let me know that I can like increment my internal circular buffer on the driver. I think that seems complicated. Let me just think about this. So we would have this on read, and we would, it is complicated, yeah. So what would that look like? We just basically say that when we are finished with the data, we are now allowed to continue. That's actually not crazy, right? You could say that you have a you could have a struct that's like TCP pointer, and this could have a this inside could hold the data, right? So this should be like a mute U8. Maybe a const U8 makes more sense. And you could send this guy through the callback, through like the connection. So you would have like, we would go back to having this channel. So receiver, TCP pointer, and this would be sender, TCP pointer. And basically I could say like on drop of this guy. So impl drop for TCP pointer. At this point, we would maybe do something that like allows this to continue. So here we would say like drop.await, right? We'd say, or we'd have something that flags to us that we've finished with it. So we'd have like TCP state tx send this guy, and we'd say like some way to wait for drop. And then we know that like we are only like freeing this buffer when the other guys are finished with it. But let's say that like the application isn't servicing this fast enough, then we're actually like holding up our entire Ethernet driver just because someone didn't parse a packet fast enough. So I think that I'm willing to take the allocation overhead. A single copy, that's fine, right? Like we're doing way more copies in other spots. If we were going for like uber high performance, we would have to consider this more. But I think for now, just to avoid the complexity, let's make it so that we send just like evacuate here. Okay. So I think that this is kind of like a reasonable skeleton for what we want to do. So we have like our server, he allocates connections. Also, I also suggest looking at IOU ring and libu ring for Linux. Yeah, that's been on the like to-do list in my head for a while. It seems pretty good. And I think that is very, very much related to what I'm thinking about now. But for now, I think I'm just gonna let's do the stupid thing first because we're so far from a working TCP implementation. And if we decide that we want to go for like higher performance later, we can loop back. That's probably what we'll do. Okay, so does this have everything that I need? We already have TCP frames. So we will need some sort of like state management structure who lives in like the kernel. That's fine. This state manager will have ways to like propagate data over to somebody who's using them. And yeah, that seems reasonable. Okay, so we have a plan. So we make a plan for TCP state handling. And this is 22 minutes in. Wow, it took a while. And next up is, I guess we need to like, we don't have any async channels right now. We don't have any like, the concept of like sender receiver isn't in our OS. So I guess we need to add one. So we'll work on making an async sender receiver. That's the first thing we want to do. So let's just pop open a new file. So it'll be like source util async channel. And in our util module, we need to use that. So pubmod async channel. There we go. And the API for, oopsies, is this spelled wrong? Channel, async channel. File not found in module. Async channel. Did I spell this wrong? Am I high? Oh, maybe I have to write this file before it's there. There we go. So what's like the usual API here? If you let's model something that's similar to what Rust's core library is. So if we look at the implementation of like these guys, well, not implementation. We don't care about the implementation, but we do care about like the API. So what they do is you call like a function, a free function, and this generates like a sender receiver pair. So we'll have that. So we'll say pub channel returns a sender t receiver t, and this takes in a t, and this is a function. Async IO is what I live for. Damn, you're crazy. That's out there, but I like it. Core ops receiver. Oh, that's interesting. What is that? What is that? Oh, experimental. Okay, we'll ignore that for now. So here we're gonna have a sender that takes in a T. And inside we're going to we'll have to think about what the implementation is. So for now we'll just leave it empty. And we're also gonna have a receiver. And for now, just so that the compiler doesn't get mad at us, we'll like mark these as having them. So I think it's like, you can use core marker phantom data, and then you can say like phantom data t is going to be in each of these. And so these are actually still like 0-size structs, but the compiler like thinks that T is being used even though it's not, and that makes everything easy. Okay, so then we would have to do construct actual mechanism. Wow, that was really poorly spelled. It's actually still wrong. Mechanism. There we go. And then we just say that then we return sender. So I guess we say like inner equals phantom data new. Or do I just say this? Phantom data? Yeah. And then we say we return sender inner receiver inner. Okay. So that compiles. Now, what do we actually want to do here? So if we're building up a queue, we need some form of we need somewhere to store the data. And that data needs to be accessible from both sides at once. So we're going to need some sort of synchronization primitive. And we're going to want these to be like future style awaits. We're going to be able to want to like await the data. So if I were going to implement this in normal like user space code, non-async, I would usually do something like sender. If I want it to be awaitable, do I also want it to be continuable? That's a good question. I'm assuming by continuable, you mean like the ability to do like for I in receiver or something, or data in receiver. I'm assuming that's what you mean by continuable versus like for while let x equals receiver dot receive dot await or something. I think that like continually equals chain async test and test that will be run after each other. Oh, I think that Rust kind of gives that to us fairly for free. Because like if I make like an async function, like do stuff, right? I can say like stuttering. We can make like a loop and say like let x equals args receive dot await, and then we can do like other stuff with x here. And so like the Rust async syntax will like automatically convert this into like the state machine that you would need. And this is like, you know, you would just write it imperatively instead of as like a method chain like you're doing in your example. Right? Because then I could say like parse file x dot await, store file x dot await, you know. Like there's no, you don't need like special syntax because it's already built into the language. Anyways, so I think that I need some sort of like await here. And what was I saying before? Oh, right. If I was going to do this in non-async code with like just multiple threads with a data and like a sender receiver, I would do something like the sender, each side would have a mutex protected queue. So you would say like your sender would have a mutex protected. He would say like Q is a mutex vec dq probably T. And when I'm waiting, what would happen is I would like wait for someone to insert data here. So you'd also have like a condition variable. Cond var, right? And you would basically like say like on the sender side, you would lock the mutex, push some data in, then signal to the condition variable that it's ready to go. And then on the receiver side, when you're waiting, you would block on this condition variable. And when it says you're ready to go, check if there's any of the data in the queue, and if there is, pop it. But we're not in normal code, normal synchronous code here. We're in like async code. So I think that this like condition variable actually just comes for free. Like you don't actually have to wait, because if you have like a future that's poll that you like on poll checks the queue, you how do I say this? That future will be polled every iteration of the event loop. And so we don't have to worry about only polling it sometimes and signaling that. So I think that we can just say that our queue is going to be a mutex, but an async mutex, vec dq. So that's use alloc vec d collections, maybe? Vec dq? Yeah. And this will be the same on both of these. And so this isn't actually a mutex vec dq. This is a mutex like rc vec dq, because this is reference counted pointer. So we want to make sure that like on both sides, it's only freed when both sides are done with it. Our mutex type needs to be imported. So we've written our own async mutex that I think works okay in single-threaded code. I haven't seen any evidence that it's broken yet. So that's in our crate. We have util async mutex. And I like these to be at the top. We also need the smart pointer type. So we have, I think it's rc here. Okay, there we go. And so now we'll say that our queue is our inner is now a mutex new rc new vec dq new. Okay. Very nice. Now we have a problem here where the sender and receiver, we need to like explicitly clone these. So we'll say sender is this guy, sender type, and his inner is going to be, oh, I have the RC and mutex swap. We want one reference counted mutex, not a mutex to two mutexes to a reference counted. So let's just pop this guy here, like this. And this guy like this. Okay. So again, we need to replace this with RC, this with mutex, swap the order. And our inner here is going to be RC clone inner. Okay. And then our receiver is going to be a receiver of inner. And then we return sender receiver. RECEIVR. I before E except after C, yeah. We need a semicolon here. Okay, we're chilling. Now we've got like the scaffolding in place. All we need to do is the hard part of implementing the sender and receiver. So I think the sender is actually really easy. So we'll do that part first. So impl t sender t. He's going to have like a function that's called send, and it's going to be async, because we need to lock this async mutex. And what happens here? He says self.inner lock await push back. And he pushes back the value that we're trying to send, which has to come in here. And that's actually it, right? Easy peasy. And then on the receiver side, oopsies, this is pub async function, not async pub function. The receiver side, all he has to do is something very similar, but pull out. So let's think. He's got a receive function. And the important part here is we actually can't write this as a normal async function, I think, because we need to define exactly what happens every time we poll. Like, how do we determine the completion? We need to like make something that blocks. So what we can do is we can say, what do we want to call this? Like receiver waiter t. And inside he's going to have the mutex, not the RC mutex. We don't need the reference count here. We can just kind of use the use it as a reference. He's going to have the queue, a mutex queue, and so we have to like assign a lifetime to this. And then we can implement a future here. So we implement future for receiver waiter. And this is for all T's, so all data types for this, we get the same thing. And we also probably have to specify a lifetime, but I think the lifetime could be anonymous, so you don't have to write the A thing over and over again. Here we need to define our output. So our output is going to be a T. Right, we're gonna like pop the, if we are ready to go, we will take that element out of the queue and give it to the caller. And so the poll function is first going to try to lock the mutex. So he's going to call this guy. He's going to poll him with the same context that we're using here. We actually need to pin him because there's just like details here about the fact that when you generate a generate a future, it's going to be like a state machine, and the state machine needs to assume a constant location of memory. So you need to like use this compiler trick to make it pin, which is like that you can't get a mutable reference, you can't do like memory operations and stuff and like invalidate it, etc., etc. So we'll say let inner equals core pin self inner, and this will make this like something that we can work with for a second. Then we poll it. Oh, why doesn't it like this? Oh, sorry. Do I need to inner poll? Oh, sorry. I need to pin the lock feature. Sorry. So this is let guard is the pinned version of the lock. One second. So this is self.inner. Okay. And now we can poll the guard. So we can say a guard poll with our context. And if this succeeds, if it's ready to go, the mutex is retrievable, we can then look at the stuff inside the mutex. So we first say that the guard is equal to this like guard poll. And if this is ready, we're great, right? We just propagate that on. And if it's, what is it, pending? We return poll pending. Now we probably need to pull in a type here, so we say use core task poll. Okay, so here we have locked the mutex, and now we can look at the data inside. So we can say guard, and what is this? Pop front, and we say if we got a value, we say we're ready, right? Otherwise, we're still waiting for data, right? This needs to be mutable. But that's actually it. Easy peasy, right? So now what we can do is we can construct this receiver waiter on our receive side. And he's going to take in, the inner is going to be self.inner, like this. And we just await him. Did I spell this wrong? Receiver waiter. I before E except after C. But that's also just like a bogus rule. Sometimes you still have an E before I unrelated to the C, and sometimes I think you have CEI, but I think it's in this case CIE or CEI. Sorry, English. Okay, so I actually think that this is it. So now we can just say that the value is this, and we don't need to assign him. We just say here, just return him directly, please. Now you get in this weird state where if the sender is dropped, we'll just block on this forever. And I'm just willing to take that hit for now, right? Like, we don't have to signal drop, but it's also easy to do that, right? You could have like a result type here, and we'll just say like sender close or something, right? You could have this, and probably just in here in your poll, you would use the reference count and check if the sender is still active or something. But I don't want to deal with that yet. Okay, so how can we test this? I cannot recall if our testing functions are async right now, so let's take a look at that. And they are, in fact, async tests. So I can actually just write some tests that check that this works correctly. So we'll make a module that's only available during cargo test. And in here, we'll use our internal test infrastructure. So we'll say use crate, testing, star. And we also need to use super star to get what we want out of it. The way we define tests in ROS is for this guy is using this create test macro. And that's because we have custom behavior. We don't have the normal int main void like you would have in C. The program startup is very customly defined, and so we can't use the normal cargo test executable. So we use this test infrastructure that we can set up on our own, and so that just means that we have to write these instead of using test and writing a function. We just have to use our own macro, and so let's just call it test async channel. And the way this guy works is first he has to return okay, I believe. And I think we need a semicolon here. Cool. And now if I run cargo test, we should see, where is it? We should see in our async channel, test async channel. And if I return an error here, we can say oh no. This will now fail, and he'll say oh no, and we'll our kernel will return to the QEMU instance. He'll propagate a failure status up. Great. Okay, so what do we actually want to test here? We want to create a channel. So we'll say let tx rx is equal to, these need to be in brackets, a channel. And we'll say tx send one.await. And we want to ensure that when we call this, that we do in fact get a 1 back. And then we want to check that if we poll this guy, we don't actually make progress. I don't know if I can call poll directly like this. I'm thinking, because I don't know if you can receive the context for a I don't know if you can extract this context that's being used for the async block from within it. Let's see. Get context from async block Rust. Is there a way to get the context from within an async function? This is exactly what I'm looking for. You can use poll function from the create futures. What does this do? I think you need to make a decision to make this event-based or polling-based. So in Rust, they're one and the same, I think. Right? So what happens is you create these futures that do poll, but they only poll when something happens. And otherwise, once it receives a pending call. So here, when I run my future, they poll an event, exactly. So here, if all of my futures return poll pending, what happens is my CPU will halt, and nothing will happen until an interrupt fires. So in this case, the Ethernet driver will receive a frame. The Ethernet card will raise a line to the CPU that says wake the fuck up, please. The CPU will be hey, I got some data on the Ethernet card. And so it will run, it'll kick it out of its halt. And that will trigger a chain of events where this poll will eventually get run, because the sender will in our callback will call this send, and then this receiver will have data. So when he calls this poll, it'll return something, but it'll poll once that poll is finished. Everybody should be pending again. I think there's some intricacies there where we are kind of over polling in some cases, but that's okay. I'm pretty sure that's how like the normal async runtimes work. But instead of using like interrupts to wake them up, they're using like the OS signaling that something came in, right? You would use something like epoll, where you have like you're waiting on like 15 sockets, and when one of those sockets returns data, all of a sudden it's like time to wake up. And I think this is very similar to what we're doing here. So this is different. I just want to make it clear that this is very much different than me hot looping on a poll. This is not a hot loop. Yeah. Okay. So, but what I want to do here is in my test, I don't want to actually wait for data here. I just want to check, does it correctly reject me in this case? So I want to, they're saying, somebody's saying that I can extract a context out of this poll function. So what the fuck is this doing? Oh, that's tricky. That's pretty funny. This is actually like a really basic feature. So you pass in a function and he just passes it in. Cool. So here, let's just use future poll function. And here we have cx. And here we just want to ensure that tx dot receive dot poll cx, I think. We probably have to pin this, but we'll see. And we'll just return this back. And so here we'll say let receive poll is equal to this. Now what we want to make sure is that there's no data here. So we want to say test eq receive poll is poll pending. And here we say we have succeeded. So we say okay. We probably have to wait this. And this is going to bitch at me because I'm sure I did something wrong. So one is I'm calling tx_receive. This should be rx.receive. And here, this needs to be poll is not found in impl blah blah blah. Oh, because I need to pin it. So pin new and mute this. He doesn't like that, so core task pin, I think. Or is it core pin pin? Core pin pin. He doesn't like that. Probably because I forgot to use the pin macro. That compiler error was just like bogus. So we actually want core pin this guy. Poll is not found in this because I put an extra mute on here. Okay, we're very close. We just need to use futures future now. Why? Let's just double check that. Because poll is part of the futures crate. So is that, I think it's core future, not futures future. And we're very close now. There's just no implementation of equal for this like task poll, which makes sense. So here instead we'll just say, we'll match what we got out of this. Or we'll say if let poll pending. No, not poll pending. Poll pending is the success case. The failure case of this is ready. And we'll say we'll test true. I guess here we'll just return an error. And we'll say async receiver had data when it shouldn't. Okay. Okay, so now this test should pass. Expected integer found poll. Oh, because we awaited this? Oh, does this not do what I want? I was kind of hoping I could like poll it once and get the value out of it. But this actually is going to poll this forever. Let's think. So we can get the value here. Sorry, what is this poll function? This poll function returns a poll function that implements future. Which means we can actually just say futures future ready the value. So we can say like the value is this. We can extract the value from the future by immediately returning it. We say that we await, we're chilling. I think. We forgot a semicolon, of course. And expected poll found ready poll. What doesn't this like here? Futures, future. There's a way to just like immediately say we're ready. Yeah, ready. Oh, we have to await this. Maybe. Target test? Fuck. Only allowed inside async function. So this is not async. Come on, man. Okay, so 76 is where the bug is. And he's expecting a poll. Oh, oops, so we just say poll ready. There we go. Solid. Okay. And now our tests are all passing. So that's a good indication that our queue is working as we expect. Yeah, okay. So now let's say that this is done, right? We've kind of like tested it very weakly, but I don't think we really need more than that. I think the fact that it's not blocking definitely is a good sign. Okay, so the next part of the plan, what was it? The next part of the plan was to track TCP state in some like structure, and our TCP connection is only this like channel. That makes sense. So I guess what we'll need to have this like TCP structure, and in him, he is going to have this state lookup. Sure. Okay, so we'll go into like network. This is getting complex enough that it's worth splitting out a sub-module in network for TCP, I think. So let's just quickly do that. So we'll go to the source, we'll go to net, and we'll now make a directory net instead of using this file directly. And this gets renamed to mod.rs, and that's the way that like Rust handles multiple files in a module, or submodules, I guess. So let's just double check this compiles. Right, we still compile, great. And now in here we can say pub mod TCP. And in source net, we now make a file called TCP. And we need to start propagating our current TCP stuff out there. So let's take this TCP flags, generate TCP flags, TCP frame, TCP, all of this stuff gets moved into this TCP submodule. I'm presuming UDP is also on the agenda. We already have UDP to some extent, but since UDP isn't so stateful, you can kind of get away with doing less. Right now, our UDP implementation, we have the ability to send a UDP packet to a specific IP port pair. And we have the ability to print out received UDP ports, but we don't have this same like we don't have the way to like forward it to application state because we haven't like wanted to do that yet. So yeah, I guess is it on the agenda? It should be. At some point, we're gonna have to give UDP the same treatment. You're right. How about Quick? Oh, I'm so far from that. I don't think Quick isn't like a new protocol, right? Quick is just HTTP over UDP, isn't it? At the application layer. I think that this is like something that your OS doesn't implement, is my understanding. Yeah, you can have it like in Chrome. Quick was developed with HTTP in mind. I think it's just UDP. Based on IP layered with UDP. Transport layer. Oh. Okay. Interesting. I thought, yeah, I know it's a protocol, but I thought that it was a protocol that you would usually implement in like applications, not like in your kernel. Because it's on top of UDP. Anyways, that's definitely not on the agenda. Maybe someday, but we're far from there. Okay. So we go into TCP RS, and we then copy paste all of these imports from the network side to make sure that everything still compiles. And we need to use create net IPv4 protocol and calculate IPv4 checksum. Calculate IPv4 checksum. Or I guess we would not, we would just use, say, self. For free functions, we don't import them directly, we just prefix them like this. I think that's the Rust style. Okay, so we've moved some code around, a bunch of imports will fail. So let's see here. The first one is that TCP frame isn't imported in the net module, so we'll net mod rs, and in here we will use TCP frame or something. What are we missing? We're missing TCP frame. So we'll start there. Cargo check. Cargo check. Okay. We're missing some imports in main. We'll deal with those in a minute. Main, everything in here is main. Here we're missing net mod. So TCP frame new is private, and we kind of want to keep it private because we don't want anybody to be able to construct this guy. We only want to be able to construct him from the TCP or from like the network layer. But I think that there's like a pub super that means that like only our parent module is allowed to access us, which is coolio. Now we have like our main cleanup to do. So generate TCP frame is going to be net TCP generate TCP frame. Oopsies. And I think this is going to be same. Net TCP generate TCP flags. This is net TCP flags. And why is it still mad? We're missing some bad imports at the top of main, so we have TCP flags params. This is here we're gonna need to add in some like TCP and pass these guys in there like this. I think. Are we good now? Cargo check. Good, we compile, I think. Cargo run. Yep, we compile and run. Oh. Yeah, okay, we're still running correctly. And now, we can go into our TCP area and we can start handling, like, implementing like a TCP table. So, we'll make a struct that's like TCP, we'll just call it TCP. And inside, what's he gonna have? He's gonna have a bunch of states, right? And probably like a hash map is probably reasonable here. And inside, he's going to be like a table of like IP port pairs. So like, he's going to have like a U8 or IP adder and port. And this is going to be mapped to a TCP state, right? So we have to have like a struct TCP state so that this compiles. And we need to import hash map. So this comes from the hash brown crate. So this is use hash brown hash map, which is the implementation of the standard library. We're just kind of cheating and pulling it out because we don't have the standard library. Okay. Cargo check, just to make sure that we're all hunky-dory, nice, everything's good. And I guess we just start pulling out what was in our TCP state, in our dummy, in our like sample code. So here, I guess we'll have to, like, since, thinking. So this actually can't be just the IP address and the socket, because, let me think. If on my sender side, or on my, like the client tries to connect to me, and he tries to connect to me 2 times, he crashes the first time and he starts again on the second time. Those are just going to be remote IP port pairs there's a chance they could overlap. But does that matter? No. And I was going to say, like, can the same remote IP and port connect to two different ports on my side? And I think the answer in the case of a crash on the first one is yes. I think that they could, in fact, try to connect to different ports. So I think that we don't only need their IP port, we also need our IP and port. Because in theory, we could also have two network cards. And if we had two network cards with two different IPs, we could maybe be serving multiple different things on those two IPs. Okay, but in TCP, that shouldn't matter, right? Well, what I'm wondering is, how do I map, right? Like, I need to flag to my own system that we need to start from scratch. And so what I was thinking is that I would start by having like pairs of their IP port, my IP port, and then if I don't receive, like, there's probably some cleanup that I would have to do eventually when a connection is dropped and they don't signal to me correctly. But at least, like, in that case, I wouldn't be trying to reuse a broken existing connection. But I could be wrong. But for now, I'm gonna start there, and if I find out later it's unnecessary, we can always back out. Should I just have a pointer to the hardware device to have your HAL functions in your TCP library called up on? I think that there's no hardware layer here, right? I think that this is, like, I'm not using any network card. I'm not using cards for TCP. I'm using cards for, like, Ethernet, and then everything TCP related is happening in software. Because even if card A crashes, card B is totally independent of that state. Yeah, I agree. But I'm just saying that, like, I need to know which card the socket is trying to be mapped to, I think. Right? If I'm serving one web server on card A and another web server on card B, I think that's, like, a valid thing to do. And depending on who the client is trying to talk to, I might want, like, I think that I need to map to different spots. All I'm saying here is that a remote IP port is not sufficient. Maybe it might be, but I think I'm just going to err on the side of caution here and just start with making a key here. Remote IP is an IP adder. The local IP is an IP adder. The remote port is a U16, and the local port is a U16. We derive hash so that we can use this as a key. I hope that derive hash exists here. And then here we use the TCP key instead of this. And sender doesn't exist, so we need to use our crate util async channel sender receiver. And those aren't public right now, so we need to make them public. So we go to util async channel, and this guy gets a pub. Oops. Pub, and this guy gets a pub. No, not this guy. This guy down here is receiver. Oh, I haven't written down what we're working on. So what we are working on right now is propagating. Yeah, TCP state from Ethernet to user. Put user in quotes because there are no users. There's no user space. There's only the kernel, who is me. But there's a useful distinction there to be made. Okay, so this TCP state has a sender. And now we want to, like, create a socket, right? So in our TCP handle, we're going to have, like, some function. Create socket, or listen maybe is a good word for this. Is that what they use in core? TCP listener. Right. They don't have a function listen. They have a TCP listener, and this presumably calls into libc to do some sort of syscall, but listen is, I think, the common terminology for this. So when we listen, we're going to get back a TCP listener. Let's use the same terminology. We will have a struct TCP listener. And I don't know what he has inside him yet. Presumably he has nothing. I was gonna say he needs to retrieve some data, but he needs to know when a connection has been established. So I guess he's going to be he's going to have a receiver of receivers, actually, right? Because he doesn't get the buffer. He gets maybe a buffer, a receiver. Doesn't make sense. He's gonna get a new TCP connection, right? When the Ethernet driver looks up the TCP state, I shouldn't say Ethernet driver. When the packet callback looks up the TCP state and sees that we've handled the syn-ack handshake, we now have a TCP connection that's ready to be written and read from. So at that point, he will send that new connection over to the current listener, and he will propagate that out. So this guy is going to return a TCP listener, and this guy is going to return TCP connections. We don't have a TCP connections yet, so we'll stub one out. And for now, he's got nothing in him. Okay, cool. So this guy, he needs to listen, but he doesn't just need to listen blindly. He needs to listen to an IP and a port. Thinking. So the port's a U16. And that means that there's actually no TCP state yet for these, right? Because we don't have the remote pair. We actually need to also have a list of things that are ports that we're listening on. So we'll say listeners is a thinking hash map, again, probably is reasonable here. And we'll do the same thing here where we won't have a TCP key, we'll have a TCP listener key, and he's just going to remove the remote parts, keep the local parts. TCP listener key, and this is going to go to TCP listener, I guess. Thinking. We might actually need some independent state here, or I guess we still have the TCP state here. We still need to know if we're in where thinking. When we get a syn, we send back a syn-ack. That is when we initialize the TCP state. Then we get the ack, and we are ready to create a connection. So we would first, I guess in here, we would have a list for each port that we're listening on. Say 10 people try to connect to us at the same time. We could have 10 in-flight connections that are not ready to go yet. So that means for each listener, we have a bunch of TCP states. And let's just first punch in what that would look like. So this would be a hash map of TCP keys to TCP states. And then we're kind of just regressing back to this hash map. So maybe this TCP state also has to have maybe this isn't a struct. Maybe this is an enum, right? And one version of him is connected like this. And this is the state for a connected one. But there's another one that's client syn. And once the client has, or syn-ack, we'll say, we've sent a syn-ack. And in this case, what do we have? We have this. Only the sequence number in the ack num. And how would we propagate that state back to this TCP listener? I guess here we would need to have a TX sender TCP connection. And so when he is ready to go, we send it. And I guess, yeah, that seems reasonable. I think. We'll find out. We'll discover the problems with this approach as we implement. Okay, so what does this guy create when he listens? He inserts into here, we'll have listeners, which is a hash map of TCP listener key to TCP to a sender of TCP connections. That seems reasonable, right? So listeners, when we say listen, all this does is it doesn't actually do anything in regards to the network. All it does is register a listener with the TCP subsystem, and then when an external client tries to initialize a connection with that port, we'll know who's listening for those connections. So I think that's reasonable. So first we say self.listeners insert. This needs to be mutable, but it actually doesn't need to be mutable. It being immutable will be a problem later, but we can handle that as that comes up with a mutex eventually. I think I just want to confirm that it will be a problem first. And is there not like an insert thing here? Sorry, let's just first we need the channel, so we'll say txrx is equal to channel or async channel, which means that we need to import our async channel module. Okay, so we return our return is a TCP listener with rx, and we turn ret, and then we insert the tx side into these listeners. So we say self listeners insert. So I don't understand why insert isn't allowed here, but I guess we'll find out. So the key will be our TCP listener key. The IP, I guess we don't have local IP and local port, we just write IP port. And that lets us just shove these in like this. And the key is the listener key, and the value is tx. So what does he like here? Insert exists, but oh, we need to implement EQ and partial EQ for the key. Of course, because our hash map, the hash is, there could be a collision, and so on collision, we need to check if this is actually the same value or if we need something else. Okay, so I think that's it for our listener setup. So let's start stubbing into main what that would look like. So in our demo, we would want a, we'll make like a new feature. And this feature is going to be called like handle TCP connection. And in here, let's say that we create a listener. So we'll say self or kernel. We're in the side our kernel. So we have self TCP listen is going to be the first thing we do. And we don't have a field TCP in our kernel, so let's shove one in there. We need to import TCP for that to work. So here we're going to have TCP. And here we're going to have like a pub function new, which returns a TCP. And this just returns TCP with listeners that are default, empty, and the states are also empty. Right? Nothing's happened yet. Bing, bang, boom. Okay, so now here on initialization of our kernel, we just say let TCP equals TCP new, and we shove this guy in here. Eventually, we'll need some sort of like hierarchy to our kernel so that we're not just shoving everything in like the root, but we only have a few things right now, so it's still manageable. And now we need to provide the IP import. So we have a static IP here. So we'll say static IP. And our port, let's just say we're going to listen on port like 889999. Sure. And we actually look like we're compiling here, which is good news. Oh, private type. Which part is a private type? TCP listener, probably. Okay. So now we have a TCP listener. And I guess we'll have like a connection API. And he takes in, he returns a connection, a TCP connection, asynchronously, right? He just sits here and waits for one. And that just says self rx receive dot await. Easy peasy. So while I just loop here, and we say that we wait for a connection. So we say let connection equal listener dot connection dot await. Connection is a private method, so we go back to TCP and we make that public. Pub async function, I think, or async pub. Pub async. Okay. There's still TCP connections and private type, so we show this guy as public. And we are compiling again, which is great. I guess we can also make sure that we run still, and we still are running. That's great as well. And what happens on our connection? On our connection, we're going to say connection write hello, and let's make him write byte strings because we don't know that we're going to be sending text. You could send anything over TCP. Text is just a good option. And let's put a new line in there. So now we need a write function on TCP connection. Actually, our goal today is not writing. Our goal today is receiving. So let's call this read. And if we get something, we'll print it. We'll say info received TCP data. Like this. This needs a thing like this. And now we need to implement the read function. Now this gets a little hairy actually, because what we would normally do is in a like conventional situation, you would actually spawn a new, well, I shouldn't say you would, because there's a lot of reasons you wouldn't do this, but you could spawn a new thread for every connection and read them. What is actually happening in this async block is we are we're blocking all future TCP connections on this one. So that's a problem, but we're just we're gonna handle that later. I'm just saying like out loud so that you guys aren't watching me being like, Mick, what are you doing? I'm very aware of this, and I think that what you would do is you would, in Tokyo, they have like a Tokyo spawn method that says like put this onto the runtime. Or you could maybe do something a little fancier where like internally you use like future combinators. There's like a way to like shove them all together, right? You could move this connection into a like vector of connections, and you could wait on all of them at once, like kind of like epoll style. Anyways, I'll figure that out later. So let's go back to TCP and we'll implement this read function. So we have a pub async function read. He does something, right? What is he going to do? He's going to wait for data from this sender. So he's going to have an RX receiver that is that receives vectors of U8. And all he's going to do is he's going to say self.rx.receive.await. And that means this guy needs an await on him. And what doesn't he like now? This cannot be formatted with the default formatter because it's a vector U8, and he is expecting a vec u8, but he got nothing. Oh, I see. So this needs to be vec u8 here. We would need to return the buffer from the read function. And this guy will just, for now, will format this as a string with the knowledge that if externally we send something that is not a string, this guy's going to lose his fucking mind. Undefined behavior, but that's okay. Okay. So weirdly, everything seems to be like coming together. If we cargo check here, everything's compiling. Very nice. Okay. So now I actually think that the like user side of this is done. And we just need to start handling like the packet callback side. So we have this handle packet function right now. And I guess one of the things that he's going to have to take in now is also going to be a handle to the TCP thing. Which means here, we need to pass in TCP here. And in here, we need to pass in self TCP. And now we're getting into this state where we knew that we were going to be in trouble due to multiple users because the listen call requires mutable access. So let's just make interior mutability here. I think that's easiest, and I think it makes sense. So all we'll do here is we'll shove this guy behind a mutex. And then we will import the mutex, which means that this listen function now needs to be an async function. And we need to lock this guy, await him. And now we need to wrap this guy in a mutex. And then in main, we have to await this listen. Okay. Okay, and this can now be immutable. There we go. We're back to compiling, I bet. Oh, I'm off. Because in this TCP thing, we forgot a comma. And now we have to just finish stubbing in these handle packet calls. So here we pass in TCP. Here we need to pass in TCP. And here we do nothing with it. We're back to compiling. Very nice, very nice, very nice. Okay, so this is where we were handling all of our TCP stuff before. So we have this like handle packet call. This gets called, we like talk to our Ethernet driver. And we say every time you get a packet, we just call handle packet. In here, we're doing like, we handle ARP to like do address resolution. We handle IPv4 frames, and in here we print something when we get a UDP frame. We also have this like sample, just like if somebody sends us a UDP exit, we just crash our kernel. Why the fuck not? And then we have this like kind of nasty TCP frame thing. So I guess, let's see. Probably what we can just do is here we can just say pub async function handle TCP. Let's think about this. And he's going to probably take in a TCP frame and return a TCP payload. Does that make sense? So I get a frame that says like, I am a new SYN request, and I just give back a frame. Here's a syn-ack. That seems pretty fucking reasonable. And then it can still be the caller's responsibility to send that to the right person, so I don't have to like pass in my Ethernet driver here and like pollute this namespace. And that would like also is just like a very unit testable thing. I think that all kind of like lines up pretty nice. So here we'll send back an option of vec u8, right? And I guess, is there any case where we get something and we don't need to return? Plenty, right? If somebody sends us an ACK, we don't do anything. We just like, okay, sure, we update our internal state and we don't send anything back. We're also not handling that case right now. We're only trying to handle reads right now, but that's fine. Sure. So what is this bitching about? Cargo check. Mismatch return type. So for now, we'll just say none. We're back to compiling, I think. Yep. And now in our main function, which is where everything lives right now, we just say instead of response frame is instead of like generating response frame here, if we see a syn-ack, we say let response TCP frame is equal to TCP.handle. Handle TCP seems like a funny name here, calling in here, so we'll say like handle frame, and we'll pass in the TCP frame. Right, and basically all of this shit will just go into here. This takes in a TCP frame. Probably by reference is what makes sense here. We don't actually need to consume the frame. We can just look at it. We can like remove all these TCP prefixes here because we know that we're working in TCP. So we'll just go like this. Okay. And then we say here we would return some response frame. Else none. Okay, and so we've got some problems here where we need to inject the source and destination addresses into our response frame. And that's not because the TCP frame actually contains the source and destination address. It's because here, we'll pop open Wikipedia here. TCP, Transmission Control Protocol. So it's because there's like a checksum field in here, and this checksum is calculated assuming that there is it mocks out an IPv4 header. So the checksum is actually related to the source and destination address and the protocol and TCP length. I don't really know why they do it this way. Maybe this explains it and I didn't read it, but it just means that in order to calculate the checksum, we need to have the source and destination address, even though the TCP frame itself doesn't include them. So we'll just pass these in here as well. And this is going to be an IP adder, and the dest IP is also going to be an IP adder. And here we'll just pass in source IP and dest IP. And should we take these in by value or by reference? Normally here, I would say by value because we're storing them somewhere. But in this case, it's like we're only using them, we're only copying them if we are in this like very specific case. So I'll take them in by reference and then copy them at this point, which I think is fair enough. Fair enough. So that means here, instead of calling all this stuff, I can't call handle TCP frame, and my source IP is my static IP. And my dest IP is the IPv4 frame source IP. Why is it saying there's a method with similar something? Cargo check. Let's see what it's bitching about. Oh, it's called because I renamed it handle frame here, but not here. Very nice. So I need to put an ampersand on this guy. And then I say if let some response TCP frame is the response TCP frame, i.e. did we actually say that we want to send something? Then we do this stuff where we actually send it out. And then otherwise we just print the data in the frame, sure. That's obviously not what we were going to do forever, but that's what we were doing before, and that's what we can keep doing for now. We forgot this guy. And what doesn't he like here? If let this is this. What is he complaining about? Cargo check. Oh, I have to await this guy? Why? Why is this an async function? It doesn't need to be. I just probably wrote async out of habit. Okay, there we go. And then let's cargo run and just kind of see if like the existing demo still functions. So here we did receive a packet with data test. We received an IPv4 frame, received packet with data test. So yeah, we are still getting TCP frames in, and we're parsing their data, which means that our like handshaking is still working correctly, which is pretty cool. Pretty cool. And now we can start handling like everything a little better. So what was happening here is we're kind of just raw sending responses back without considering like the state of the connection. So what we actually have to do here is the first thing we need to do is we need to look up the current state. So we can say that our current state is the TCP states entry, I think. There's a like, how do you, there's an API to like get or insert, is just essentially what I'm looking for. So let's look at this guy. So there's a hash map, and on him, I'm certain that there was like an entry API, but maybe the entry API is only the standard library and the, oh no, here we go, entry. Yeah, here we go, this is what I'm looking for. So it gets the given entry's corresponding entry in the map in place for in-place manipulation. Right, so the idea is that we can, once we have this, it's like either occupied or vacant, and then we can do like a get or insert here, right? Very good, very good, very good, very good. Okay, so we can start by saying, hold on. I got lost. Where am I? So I guess the first thing we need to do is probably those APIs aren't available because they're mutating. So we'll stick this guy behind a mutex as well. And we'll say that the state is TCP states lock, right? And we have to await that, which means that this actually does need to become an async function again. And then we can look at the entry for the key. So we need to create a key from this frame. So this key, TCP key, is going to be a TCP key with the remote IP, source, dest IP. Local IP is source IP. Remote port is frame dot sender or port, source port, right? Because the sender is giving this to us, and the local port is frame dot dest port. Now we look at the entry with TCP key. And what are we missing? What are we missing? Cargo, okay, so there's a couple of problems here where these guys need to be dereferenced. And let's look at what it doesn't like here. So entry is not found. Oh, because TCP key also needs the same state here with the same treatment where we give it ways to resolve hash collisions. Very nice. And this guy also needs to be in a mutex now. And there we go, we're getting close. So we have to copy this guy into the entry API. And then we call get, there's like a get or insert. So what is this guy? He returns an entry. And I think there's just like a or insert. And what do we insert here? That's a really good question. So we need to create a new TCP state. So maybe our initial state is going to be unknown or uninitialized. And then in here, we're going to like handle TCP frames differently depending on which state we're in. That seems pretty reasonable. So first we are going to insert this uninitialized state, which is TCP state uninit. Right? Is that what I wrote? Yep. Let's just do a quick hard check. So what is he unhappy with? Because I called getter insert with instead of or insert. What's he complaining about now? He doesn't like that I didn't await this in main. So here we need to await. And now he's compiling. Very nice. Very, very, very nice. Okay, so now we can match our state. And depending on the state, we will behave differently. So our current state is going to be uninit. So we say match state. And if we're in TCP state uninit, we then assume, like, we don't, anything that's not a syn request, we reject, right? We just do nothing. I think that's pretty reasonable, right? So they're sending us, like, they're trying to, like, send us normal data because they've held onto a connection and our kernel's rebooted. We just don't answer them. Say fuck off. Probably there's, like, a more reasonable way to handle this, but I think that that's what I'm going to do for now. So we'll just say that, we'll look at the flags from the frame. And if the flags are not syn, so if there's not flags syn, return. None. Nothing to do. Is that reasonable? Thinking. Yeah, sure. Then we can say if flags ack, we also return none. Because like they shouldn't be sending us a syn-ack, they should also be sending us a syn. But I actually don't know all of the cases that this is gonna fail, and I don't even know if I should reject these. So we'll just pretend that if we get a syn, it's a syn. Now we generate our response frame for the syn. Right? Like this. And we can initialize our sequence number as we want here. Like we can actually like, this is, now we're like hard coding this. Great. And that's fine because this is an uninitialized connection. So we don't need any of the like existing state to get there. To get the right output. And now the question is, what do we do now? We say we want to like transition to the next state. So, let's see, what is the type of state here? So here we need to say that we're going to do nothing for the other states, just so that it compiles nicely and we can use our thing. So our state is a mute TCP state. So we can probably just reassign the state inside. So if I say like state is equal to, now we have a syn-ack sent state, right? Syn-ack sent, and our seek num is response frame, we don't actually, the response frame is just a bunch of bytes here, so we actually need to hold on to these things. So we'll say seek num is equal to net rand. Now this is actually not a random function because we have no like entropy in our system, so I just initialize with the same value every time. And we'll make our ack num is equal to the input sequence number plus one, because that's what the Wikipedia page said it to be. And now here we can say our sequence number is this and our ack num is this. And now we, I guess, need to associate this with the listener. Is that correct? Yeah, so we actually have to create a connection somehow. Do we? No. We actually don't have to create a connection until we're connected. So we update our state for this. And we want these to be U32s, not U sizes. And then we return the response frame. So we return some response frame. And now, next time, we're going to like get an ACK back from this guy. Shit. I actually can't update the state from within this match statement because I'm already using it, so that's fucking annoying. I'm assuming cargo check. Oh, he actually doesn't like this, so this should be a I think we just have to do, we say let TCP states is self.tcp locks await, and then we could say let state is equal to TCP states entry. And this is to be mutable. And there we go, we're compiling it. Very nice. Now, we are now in syn-ack sent, and we now want to receive an ACK. So we just say here that if we're in the state syn-ack sent, we're expecting to receive an ACK. But I guess, like, theoretically, we might need to resend the previous syn-ack, even if we're in this state, right? So really, if we are in this state and we receive a syn request, we have to reset. So we can say that our state is, so if we receive a syn, we set our state to be TCP state uninit, and recursively send a hand, we pass it, we call ourselves again. I think that's reasonable. Thinking. Okay, so what doesn't he like here? He doesn't like that I haven't used the stuff inside. And now what doesn't he like? We can't... We have to await this, probably. And, recursive async functions. Oh, you can't write recursive async functions! Fuck! Ugh. That's annoying. That's annoying. Consider using the async recursion crate. Async recursion on docs.rs. What does this guy do? Oh, you just drop an async recursion macro on top. I'm assuming that the conversion is actually not that hard, though, right? Instead of calling async function here, you say function handle frame returns a boxdine future, where the result is this. I don't know if it's result or output. Output, I think. And I'm assuming that the reason you have to do this is because the state machine that you would generate for the async function with recursion just expands forever. And so putting it behind like this like heap allocation kind of fixes it. So all of this just goes in a box new async, and then you just shove all this over here like this. Cargo check. Okay, so there's some problems in here. Problems. So I just need an extra bracket here. And now he doesn't like that response TCP. Oh, it's this. I need to use alloc box. So here I add the box to my imports because we're not in normal Rust where all this is imported for us automatically. We have to import it ourselves. Okay. And what doesn't like now? Well, we're not using future, so we import core future. And we actually don't want to just return a box. We want to return a box pin or a pin box. We'll write pin here and we'll see what it wants. It wants found pin box. It wants pin box. Look at that sick type. I love it when you have like 1, 2, 3, 4, 5 angle brackets back to back. Okay, what's it bitching about now? So something. Oh, it's because fucking core pin isn't imported. So here we just add a pin. And we write comma. And fuck. So all of this stuff is now broken because of the lifetime bounds, but we can just add a lifetime constraint on here, like it said. I think it was, oh god, on this one. I think. No. So this is 1, 2, 2, 1. I think this one. So it actually is still quite angry. I guess so we can constrain all of these lifetimes with a name. And hopefully, if I say that all of these have to be valid for this time, your output also has to be valid for this time. Let's go! Oh, lifetimes in Rust can be so frustrating, but it's nice when you guess correctly. Guess is kind of strong, but it's nice when you get them right. Okay, so that handles the case where we're like on a reset. What happens if we get an ack? So let's say that we return none in the case where we don't receive. If we've sent a syn-ack, the only thing that should be valid is an ack. And if we get an ack, then all of a sudden our handshake's complete and we can make a new connection. So we have two things that we need to do here. One is we need to construct the connection. So let's start there. TCP connection. So we'll say let tx rx is equal to connection. This is channel, I guess. So async channel. Our connection has this rx. And we actually need to validate that our ack is the correct number, and we need to update our internal state. So let's double check what happens there. So we have TCP on Wikipedia, which is already here. And somewhere we have connection establishment. So he sends an ack back to the server. The sequence number is set to the received acknowledgement value, and the acknowledgement number is set to one more than the received sequence number. And I assume that after that, I don't think I need to write these down anywhere. Probably I need to write down the received sequence number. He sent me this, and he's later going to send me B+2. So I need to write that down. Or maybe I need to write down the sequence number. One of these I need to keep track of. Actually, maybe both, right? I have to keep track of if he received what I've sent. So I guess on send, I have to increment the sequence number, which I do, which is set hard-coded right now. And I also have to keep track of his ACNUM. Let me double check where ACNUM comes from. ACNUM is the incoming sequence number plus 1. So I guess what I'm tracking is I'm saying when I send my ACK, I'm saying like, this is the next thing I'm okay to receive, I guess. And so here, I probably have to increment my ACNUM again. Well, I'm thinking. No. He's going to send back the number I sent. So I sent him I sent him an ACK of a plus 1, and he sends me a plus 1 back. So I'm saying, hey, when you receive this packet, send me a plus 1. And he did that. Which means that I can write down that I got it. That seems reasonable to me. So, I need to make sure that the ACK number is in fact 1 plus what I have. So I look at my state, which is ACK num, right? And so I will make this mutable. And we'll ensure, so we'll say if ACK num is not equal to, if the received ACK num, so flags sequence number is not equal to ACK num plus 1. For now, I don't really know what I want to do here. So I'm just going to write an error. Sequence number not expected in syn-ack. And I guess probably I'll say expected, or I'll say ACK num is this, and seek num is this. And then here I'll write down the ACK num and frame.seek num. And at that point we return none because we don't know what the fuck's going on. And now we can assume that they sent us the correct ACK num, so we can say ACK num plus equals 1. Right, this is what we should expect to receive next time they send us something. Or next time they receive something, sorry, from us. They should ACK with this new ACK num, I think. We'll find out. And here we've created a connection, and so now we can look up our listeners. And we will just send. We have to look up, so it's a get, I think. And we need to use our TCP listener key. So this is, what does this guy need? He needs an IP, which is our IP. And he needs a port, which is the frame desk port. And if we see something in there, so we'll try to get that, right? We'll send in our listener key. This guy can't be dereferenced. Oops. And if we get something, I guess we need to match this, right? And if we see some x, we return x, and if we get none, we say error syn-ack for non-existent listener, and we return none, right? So basically, like, this is like a poor man's firewall, I guess. We don't actually like talk to TCP that isn't associated with us. I guess theoretically this should happen up here before we even send a syn-ack, right? We should actually do this here. But fuck it. I'll handle that later. I just want to like work through this here first. So now at this point we know that there's a listener. So we can actually send our connection out to the listener. Right? We need to do a little bit of Rust lifetime massaging here. So we move this guy up a row so that he's got like a variable binding that lives for a little bit. We send the connection here, and then I guess we also need to store the sender side for us. So this is going to be a connected, right? Once we've received the correct ACK, we are moving our TCP state from syn-ack to connected. So here we'll say state is equal to TCP state syn-ack or connected. Our sequence number is going to be the current sequence number, and the ACK num is going to be the current ACK num, and TX is going to be TX. Easy. So now we just have to make sure that we write down seq num here. And I think we're getting pretty close. Okay, so we need to dereference the borrow. For some reason, only for seq num, but not for ACK num. That's weird. Probably because the mutable makes it like a copy and the immutable makes it a reference. Maybe. I don't fucking know. And once we've updated our state, we pass on our connection. And when we receive an ACK here, do we need to return anything? And the answer is no. We do not. And now we're pretty close, actually. All we have to do now is if we're already connected and we receive data, we can just I think we just send that on to the application or the user. So let's see. So we have the frame payload, and I think we just send that. And I guess we also have to ACK what we received. So here we have the sequence number. And I guess we have to send back. Probably we'll have to update our sequence number internally and ACK it. But I guess for now, let's just, before we get crazy here and start trying to handle that correctly, let's just see if we get the data. Because this is like a really good checkpoint for something interesting to be shown on screen. So yeah, let's just try that. So here if I cargo run, we're close. Okay. So let me look at what we're doing here. In main, we have on receive. Or I guess we're handle packet. In here, we are passing on our received shit into the TCP subsystem. We don't want to log here anymore, like we were before. And in main, in our async function, we have a handle TCP connection, and here we want to see this log, which means that we need to do a futures future select. I guess we need to join receive and handle TCP connection, because the idea is that we want both of these guys to go forever, and this guy handles like waiting till the end. Cargo check. Let's just double check what's pitching about. So he doesn't like that this guy isn't pinned. So we'll say that handle TCP connection is a pinned version of handle TCP connection. Okay, we compile. And what we want to see here is we want to see a log that we received data. So let's see. We are not logging really anything interesting. So let's take this loop out and just try to see if we can see what we want to see. Okay, so what happened here? We received an IP frame, and then we got sequence number not as expected in syn-ack. We expected 1 greater, and we got the same. So let's just double check here. So that's this error. So let's just say sequence number is supposed to be ACK num. And let's see if that behaves a little more sanely. So we got a syn-ack for a non-existent listener. That's really good. That's really good because we're sending to 6,000, but we're listening on 9999. So we'll do a cargo run here again. Send to 9999. Oh, baby, let's go. Okay, that's fucking sick. So we now have gotten to the point where, oh, that's so sick. That is so sick. So here we have this like pretty reasonable API that's being used from our kernel demo that just says like, I want to listen on this port and like driver side, do whatever the fuck you want. Just like tell me when I get some data. And so we like listen on a port and we get a connection from that port and we try to like write that data out. On the TCP side, we are like migrating ourselves through this state machine, propagating these like types around to get through to the point where we now know internally that we've like completed our TCP handshake, and now we're like we're like propagating that data onto the like kernel demo side. That's really sick. And the only thing that's really left now is we need to make sure that we don't get like spammed with data. So I think that what we have to do is we have to send an ACK back, which I don't actually know how to do yet, but I think it shouldn't be too hard. So here we probably have like, we're going to do something very similar to the uninitialized case. Where we're going to increment, we're going to like send a ACK that is the sequence number they sent, maybe +1, I'm not really sure. Maybe just the sequence number they sent. We'll try that first. So we'll take in mutex num and seek num, and we're only going to accept this if our acknowledgement number is 1 less than the sequence number. So let's say that if acknum is not equal to frame.seeknum, we will say return none, and we'll log an error. Invalid seek num for I guess this isn't really an error. This is more of like a debug log, right? Because this could happen in like a normal lossy network. And we'll say that ack num did not match seek num, and we'll return none. Now our ack num is now greater, like increased by 1. And do we send back, which ack num do we send back? I guess we probably send back the old ack num. So probably here, we move this ack num increment down here. We update our connected state to just have all of the things that we have before, but we've increased some of them. Okay. We send the payload this, and here we also dereference seeknum. And I wonder if that's it. I guess here we're not sending a syn. We're just sending an ack, not a syn. And everything else probably just is what it was before. So what are you bitching about? He doesn't like that this is borrowed, so... Oh, that makes sense. So we actually can't... from in here, we are using like references to the connected... to the stuff in the connected state. And so I wonder if there's a way to like, we actually, I think if we want to like access these guys directly, we just have to like wrap them in new structs. So we'll just say syn-ack state is this. Unfortunately, I guess here we can leave them like that, and we'll just use the connected state. So we'll say struct connected state, and he's this guy's. And we now have like connected state in here. And now this is going to be broken all over the place. So here we say, here we say that this is connected state like this, right? And here we, instead of taking these guys directly, we have state here. And this isn't state, this should be, oh, that's fine if they're state. And now we just have to put state dot all over the place here. Like this, state dot acnum, state dot seeknum, u32 cannot be dereferenced. And here we say state.acnum plus equals 1. This is a mutable state so that we can change the shit inside it. We have state.tx.send. And here we just don't actually have to update the state like this. We've already incremented it there. And then we return some response frame. And what we're hoping to see here is we're hoping to see that we don't get spammed with these, that we only see like one data pointer sent to us now, because on the netcat side, he should get the ACK that he expects, and so he shouldn't try to start retransmitting data. So let's see what that looks like. There's debug logs in here that aren't running, so let's go into our logger initialization and just make sure that the everything we need is being logged. So we need to now add logs for TCP. And let's just see if this will now give us anything useful in our logs. Right, so acnum did not match sequence number. And we should actually probably write down what those were, because I have no idea. So we'll just do this, state acnum frame.seeknum. Okay, so we're probably just off by one here. Yeah, so we have acnum one above sequence num. And I wonder if that is what we want. So that's kind of interesting. So I guess let's look at the Wireshark dump and see how that looks. Because I'm not confident that I understand this right. So now we echo test. We should see our spam. We can Wireshark network.dump. And so here we have syn-ack, ack. Now he pushes to us with sequence 1, ack 1. And we should return back sequence 1, ack 2, maybe? Let's try that. So here I think we try this. We increase our acnum. Is that right? So our acnum. Sorry, we subtract one here. Then we send the current one, which is one above. And then we say we expect this one next. I think we're off by one this whole time. So this acnum plus equals 1, we just won't do this. And we will leave this the way it was. So I think this goes like this. I think we'll see. We'll see what he wants there. So here we have, we'll close them both, make sure that we're in a clean state. And here, we received data, but our acnum did not match the sequence number still. So let's look at TCP again. We'll open recent. So here we have our syn-ack, ack with sequence 1, ack 1. And then they push us with sequence 1, ack 1. And we ack sequence 0, ack 2. Which seems reasonable to some extent, right? we are 1 greater than we were before. The fact that we previously act with sequence 1 and now we're acting with sequence 0 is kind of fucking weird. So let's see what we sent back before on our syn-ack sent. We sent back the sequence num, which was the frame, which was just a random number. Do we need to increment our sequence number here? Let's see. Connection, termination, that's not what we want. We want data transfer. So order data transfer, retransmission of lost packets, blah, blah, blah. TCP uses sequence number to identify each byte of data. The sequence number identifies the order of bytes sent from each computer so the data can be reconstructed in order, regardless of out-of-order delivery that may occur. Sequence number is the first byte is chosen by the transmitter for the first packet, which is a flag of SYN. The number can be arbitrary and should, in fact, be unpredictable. Sure, but it's not, but that's okay. ACKs are sent with a sequence number by the receiver of data to tell the sender that the data has been received to the specified byte. ACKs do not imply that the data has been delivered to the application. They merely signify it's now the receiver's responsibility to deliver the data. Sure. Reliability is achieved by the sender detecting lost data and retransmitting, blah, 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 blah. So where does it tell us, like, what do we actually put in here? I guess we just look at our example. So here we've, like, captured a localhost TCP thing, and so he pushes ACK, seek1, ACK1. Fuck, there's like, this is like a little busted, so let's just double check. So first when we send our syn-ack, we send with 81183 blah blah blah. So what is our push ACK here? Oh, interesting. So he's got an ACK here, and then so this is the one we want to figure out here. So he sent us sequence number 112.689.4953, and we ACK back with 112.689.4958. That's weird. Oh, because maybe the data is 8 bytes long or something, and so we need to ACK that would not only, we might need to ACK like the entire payload. Now here the payload was 1 byte. Which is just a lie, by the way. I think this Wireshark dump is broken. That's fucking annoying. That's annoying. So I actually can't use this as a reference. Let's see. TCP, what are we trying to figure out? We're trying to figure out what we're supposed to send back. So let's just see what goes in an ACK. ACK number calculation. So he says sequence number 1, len 669, then this goes up. So, right, so we need to start with the sequence number and ACK the len. Okay, sure. That seems reasonable. So here, I think there's a bug. I think we're gonna have trouble here. We'll see. So we say that our ACK_num is the so we should be expecting we should make our ACK_num always be what we're expecting. Then we should add the sequence number to the data. So here our ACK_num is going to be frame.seek_num plus the frame payload len, right? Now, I expect there to be a bug in here, actually, because I think that our payload is, like, padded. So let me just double check this. Our payload here comes out as the data offset plus the full size. Yeah, so he doesn't actually do any, like, length checking here, which is going to be a problem. but that's okay for now. So let's see what happens if I do that. So we still have this problem where our ack nums don't match what we expected, so we won't return none here. We'll actually still try to send our ack back. And, oopsies, we need to now run our netcat thing. And now I've got like an add overflow issue. Oh, because we're plus equaling here, this should just be equals. And let's try this again. So we are having problems. Okay. I'm gonna do some off-screen reading, I think. I think we got to a pretty good spot. I wanted to figure out what these sequence numbers, ack numbers are supposed to be with a little bit more time reading. But yeah, I think we got in a pretty good spot today. So we kind of set up our initial TCP like propagation logic. We have this like state machine now that's being handled from like our Ethernet callback, and when we get packets we can like transition between our states, update our sequence numbers, etc., etc. And these get like sent over to a somewhat sane initial, like a somewhat sane API from like the caller's perspective. So the caller here is going to call this, like, he's going to create like a listener on a port, and he's, for each connection on the listener, he's going to like read some data from it and log it, and that's working very well. I'm pretty happy with that. So next stream we'll probably start looking a little closer at trying to make sure that our state handling is correct to the point where we don't get these like retransmissions from the client on send. And if we get through that, we'll just keep going and try to like, we'll probably like simulate some network droppage and stuff and see how that behaves. Yeah, if you liked what you saw, you can always catch me live most days at like around 2 Pacific is when I start streaming. If you missed stuff, you can catch up on YouTube. The YouTube is linked in the Twitch description. If you're on YouTube and you want to catch me live, you can catch me on Twitch. And that's also linked in the YouTube description. Thanks for watching. Catch you on the next one. Bye.